Welcome to Breadboarding. In the previous video we added our two EEPROMs here, so two 32K EEPROMs which are for putting the system BIOS in. So the BIOS is responsible for starting up the computer, testing it and then looking for an operating system. And this is using our Intel 386 processor over here in our breadboard adapter there. And in this video what I'm going to be doing is looking at how to add a power on self-test port to the computer. This is an example of a power on self-test card from a more modern era. So this has got PCI Express and PCI. However, the older ISA bus ports were substantially simpler. So this is video 19 in the 386 Breadboard PC series, and we're going to be looking at adding a power on self-test port, otherwise known as a post port. So there's a good resource for a lot of the early PCs, -0degrees.net, which I've used a number of times and referenced it. I will include the URLs in the description below if you want to look at this yourself. And there's a section here on ISA bus postcards. So POST stands for Power on Self-Test, and they were really started to be introduced around the time that the IBM PC-AT came out. Now the postcards can display numerous postcodes. So in the early days these tended to be just an LED display on an ISA bus card to plug into the PC, and generally what it would show is the various checkpoints that occurred during a power on self-test. And really you don't want to think of these as error codes, they're really more of a status or progress indicator. So an example down here just to show you, you may have one or more codes here. I think this is the last code and perhaps the second from last code. In general what this would allow you to do is to work out what stage the PC had actually powered up to if it was actually faulty. So it would normally tell you if it was having a problem with, say, the keyboard controller, floppy disk controller, something like that. And you can see on this one we've actually got the old ISA bus, and in fact there's also the PCI bus here as well. And this is an older one. You can see there's a lot more sort of older logic here, a couple of PLDs here, and it's actually got error code here, which perhaps is a little misleading. So we're really talking about status codes on power on self-test. What this would allow you to do is if the computer wasn't starting up properly, if you plugged in one of these, then if the BIOS supported it, then you would actually get various status codes coming out. And generally the last status code would give you an indication of how far it had got to and where the likely problem was. Now the I/O port which is actually used for it, the standard one is generally known as port 80. However, because we're using the COMPAQ DeskPro 386 as a basis for our project, we're actually going to be using 84. And you can also see that PS2 models then had a different port, and depending on the BIOS you were using in later PCs, then the port number could be different. And in fact, micro channel bus was IBM PS2. So the port that you needed for your postcard would need to be configured. And in fact, I think on some of these you can actually see here that the dip switches here allow the configuration between port 80, 84, 90, 300 and 680. So what do we need to do for our post port? We don't actually need an LED display because we can just plug a logic analyzer into the output, and that will actually allow us to track the status codes as they progress through the BIOS startup process. Now to start with, we're just going to be modifying one of our test programs I used in the previous video, and we're just going to get it to read the ROM and then output the data to the power on self-test port. So summarizing that info, post port shows the last post code output before a PC hangs, or you might get 00 for the OS booting. So the original IBM PC had no power on self-test port. The PC-XT had a limited one. It used the I/O port 60, which was port A, which was partly used for polling the keyboard for the keyboard output. It only included 4 checkpoint codes in the early boot process, and we'll have a look at that in a minute. The PC-AT was a computer that introduced the power on self-test port properly. This used port 80. Now that also happened to conflict with the original PC and PC-XT with the DMA0 page register, although DMA0 was actually used for dynamic RAM refresh. So there's a few bits in the early PCs which were a little conflicting, but the PC-AT included many power on self-test codes, and I think the documentation included a list of them at the end. So we're going to be using the DeskPro 386 16 design, and this is using I/O port 84. And the reason why we're doing this is at some point in the project I want to try and use the original COMPAQ DeskPro BIOS rather than the XI88 BIOS that I've been using up till now. So by keeping with the standard for the COMPAQ PCs, we'll hopefully be able to get it to work. As I've referenced in the past, Sergey Kiselev had an XI88 PCXT hybrid design, and this used port 80 as well. And the XI88 BIOS examples that I've been using actually show that, and we'll have a look at that in a minute as well. And this is the Power on Self-Test URL that I've just been referencing. So this is the PCXT I/O ports. So you can see here that in fact, because it used port 60, this was actually the parallel port interface, which is really partly used for the keyboard interface. And in fact, under normal circumstances, port A was actually used to read the output of the keyboard. However, when doing the diagnostics, there was actually an output on port B that would actually disable the keyboard and would then allow this diagnostic output to come out. But I think there are only 4 checkpoints there, so it wasn't really that useful. Then when the PC-AT came out, then DMA channel 0 was now actually using port 87 rather than the 80. And in fact, when we look at the BIOS in the PC-AT technical guide, you can see the manufacturing port, or the post checkpoint port, is in fact port 80. And then in the DeskPro 386, you can see the I/O ports here, that the port 80 is registered within the DMA page register range. 84 is again reserved for the DMA page register range, but in fact is used for the Power on Self-Test port. And you can see here, in fact, channel 0 page is in fact mapped to 87, similar to the PC-AT here. And finally, the XI88 BIOS. So this was the BIOS that I've used in the 2 earlier PC projects. This has a file that includes all of the poster codes. In fact, it's actually called error.inc. So it's not strictly correct, but the postcodes here. So you can see here that in fact, when it's starting to boot the OS, it sets it to 0. But you can see how the initialization progresses through testing the CPU, initial configuration, doing some RAM testing, programmable interrupt controller, keyboard controller, video BIOS. So you can see the stage at which it actually would fail would give us an indication of what was likely to have gone wrong. And you can see here some particular failure codes here, that if the bottom 32K of RAM had failed, then there's not really much it could really do. And so by looking at these codes, you can actually work out what was going on. And in fact, when I was doing the earlier projects with the XI88 BIOS, what I actually did when I was debugging some of the floppy disk controller sections, and in fact I added my own outputs here. So in fact, I think I included an EE code, was basically logging the read disk command, and then I actually output the various input parameters. So the number of sectors, cylinders, sectors, heads, etc. were then output sequentially actually from this. So when you're trying to debug BIOS and low-level operating system stuff, the ability to be able to output stuff to a Power on Self-Test port is quite useful. So what do we need to do to actually implement this? It's actually quite fairly straightforward. In fact, all we're going to need to do is use these 2 chips here. So this one here is a program or logic device that we'll use to doing the I/O port decoding. So this just means that it will only sort of select this particular latch when port 84 is selected for an I/O write. And this is just a standard 74LS 574 latch that we tend to use quite a lot in the video cards for latching 8 bits of data. So let's have a look at the KiCad diagram to see what we're going to need to do there. So here's where our ROMs were that we added during the last video. In fact, what I've found is I've got enough space there, so I'm just going to add the Power on Self-Test port actually here and here. So this is the latch, the 74LS 574 latch, and you can see here that all we're doing is we're taking the data lines that we've already got coming in and out for the ROMs here, and all I'm going to do is to actually take a feed for the SD0 to SD7 and put it over here, and then we're just going to plug our logic analyzer into the post port here. The signal which is used to clock or latch the data from the data bus is in fact this post write, and this post write comes from our PLD over here, and you'll see the PLD here takes the SA0 to SA7, SA8 to SA15, so the IO addresses were only in the lower 64K, so that's the maximum you could have. And in fact, I think the PC generally only used IO addresses under 400 range, but I'm going to decode this fully so that if we want to use higher port ranges, we can do. And we've also got the IO write control signal coming in there. So this comes out from our control logic here. So this will just mean that the logic rules have got here, the post write will only go low. When the IO write goes low, we've got the 0x84 address active on these inputs here. So if you just have a look at the PLD rules used for doing that. So this is a fairly simple post address decoder. I might use this for adding a few other decodes at a later point. You can see there's a couple of unused inputs and outputs here. So all we're going to do here, we've defined all of the SA0 up to SA15. We've also got our IO write. Because this is active low, in the logic rules down here, because we've got the exclamation mark there, then we can just treat IO write as always true during our logic rules. Similarly, the post write, because we've got the exclamation mark there, we can just deal with true logic levels during our rules here. And the key trick here really is if we use this address field for decoding the SA0 to SA15, then all we need to do is to say when address is 84 and IO write, this is the rule that we want. So if we just go into WinCUPL and compile that, and just compile it, that's compiled successfully. If we have a look at the documentation file coming out from there, so you can see that it's actually decoded the rules here. So you've got when IO write, and all of these ones with the exclamation mark, the rule will only be true when these are 0. And you can see that in fact the SA15 all the way down to SA8 all need to be 0. SA7 is 8, 0. And then we can see here that SA2 is the 4. So this has actually decoded the rule. So it's a lot easier to use those address field type notation. It's a lot easier, particularly if we're trying to do ranges of addresses, for example, that we might need to do later. We can see that because we've got quite a lot of the input outputs are defined as inputs, then the output enable is disabled, which means that they'll be defined as inputs. We just want to check that the only thing we've got with a 0 pin there is our field for the address, so that's okay. So this a fairly simple PLD should be okay there, and we'll just check the pin outs down the bottom. So we've got the IO write SA0 to SA7, SA8 to SA15, and then we've got our post write on pin 15 there. So just going to go and program that first. I did make the mistake in the previous video where I fitted the PLD into the circuit before I'd actually programmed it, so I'm just going to program that first. Here's the programmer. We just need to make sure it goes in the correct orientation down the bottom here. I always recommend you read the PLD or the EEPROM, whatever you're trying to program first, because if you have got it in wrong, it'll probably tell you there and then. If you try and program something when it's in the wrong way around, you may very well break it. Now we're just going to read the chip first of all. We've got it selected as the ATF22V10C. So that's read it okay. We just now need to find our GED file. So we just need to go to our PLD directory. So I've loaded the GED file there. You can see that it's largely zeros, and then there'll be a few ones and things knocking around. There you go, we have got some ones and things there. So just going to program that. Okay, so take that out of our programmer. Just going to move the camera down to here. So we're going to be putting the 574 latch there. We're going to need to take some data lines from there and there. And then the decoder is going to go in here. And because we've got the lower address lines are coming in there, the upper address lines coming in there. So I'm just going to wire the lower ones across to here, just directly, and then they're going to have another jumper cable to come over here. So just going to reposition the camera and then we'll go and wire that up. Okay, so I've just moved the camera. I've taken a few of the Logic Analyzer ribbon cables out at the moment just so that it makes it a little bit clearer. So we're going to be putting the latch down the right hand side here. So we've got the chip labels on there. We've got the SD0 to SD7. Then we've got the power on self-test port out on the other side here. So there's just enough space to plug that in there. So we'll plug that in there. Then we've got the program or logic device that we've just programmed. And the SA0, SA1, SA2 down to SA7 is actually going to be connected up to the values coming in here. So this is SA0 to SA8, SA7 there. And then we've also got 8, 13 and 15, but we're just going to move this connector in and probably this connector in, shuffle these wires around a little, and then we'll be able to wire up SA0 and SA0 directly across here and SA7 as well. We just need to make sure that we get the right pins lined up there, and then we'll start to wire all that up. So just move some of these wires around, shuffle this connector just a couple of holes in, and there's enough space there to plug a ribbon cable going over there. So let's just wire in this first one. IO right down to IO right over here. Power on self-test right from the PLD here down to our latch. Just wiring the power lines and the output enable. Now we need to wire in the SA8 to SA15, goes to SA8 to SA15 here. And then SD0 to SD7 to SD0 to SD7. So just need to check that the orientation is correct. So we have purple generally at pin 0. Okay, so that's all wired up now. So we just need to program the EEPROMs. So let's just take a look at the test software we're going to be using. So this is test ROM 3. It's the same as what I had before, apart from now we've just added the power on self-test port. So you can see here we've got the post register is 84 hexadecimal. So that's the one that we're using for the COMPAQ DeskPro. And the only difference really is we're now using this out statement. So out to the post register, the AL register. So I've just changed this a little bit. So we're reading the value from our ROM address into AL, then we output it. These two jumps will just cause a bit of delay. We don't really want to use no operation codes for delays with the 386, but the jumps should actually work a bit better. Go on to the next address and then check to see if we've got the end of 60k, and then go back round again. So we should see sort of 0 to FF appearing on the post register about 240 times, I think. So I've already assembled that, and then I've split it into the even and the odd bytes, and so we'll just need to program that a little bit later. This is the even one. That's in the programmer. So you can see this is the even bytes. The odd one, it's in the programmer. Okay, so that's everything programmed. We just now need to get another logic analyzer to put on the outputs here, and then we can actually check to see if we get any post output coming out on those data lines there. So here's the other logic analyzer I've got, so LA1010. It's a little more limited. It doesn't have any internal memory, so it can't actually do as fast signals as these other two can, but it's fine for actually reading the power on self-test port, so we'll just plug D0 to D7 there. We'll plug this line in post right, and then these two leads just need to go into the ground. We'll just plug the USB cable into that. So we should all be set. Okay, so I'm all ready to do the test. I've got the logic analyzer. This is the LA1010 we've just connected, and you see you've got D0 to D7. These are then configured as an analyzer, the D0 to D7. Then we also have the post write enable here as well, so we should be able to see each time we write the data here. So it's now a few days later. I've been away for a couple of days, but we've now got the logic analyzer plugged into our power on self-test port here. So this LA1010 is connected to the power on self-test port. These other two ones are looking at various control signals, and I'll explain the reason why. Had a few problems. The basic thing worked. I was able to get the certain amount working, but there weren't the right values being written out to the post port, and I'll just explain what the cause of that was. So this is an example of one of the traces I was looking at, and you can see here that there is the B clock 0, which is the latch clock that actually takes the data from the ISA bus SD0 to SD7 and actually clocks it into the processor data. So you can see here the 2 bytes that I've got here. If I zoom in, what this is showing here is the first byte there is the byte which is on the lower byte of the SD data bus, and the second one there is actually what the processor is seeing. And you can see here that in fact when we were actually doing this read, so what we've got here is a number of the reading the code, and so you can see here that the 04 means that we're reading code and it's actually reading all the data correctly. And in fact you can see that the bytes there on the even bytes, these are actually matching, which means that the clock signal here is actually clocking the data from the ISA bus SD into the PD. So we can see that SD and PD are equal. However, when we come to do the memory read, so this is actually reading from memory for data rather than for code, then in fact we'd expect to see a green sort of bump there, which is the clock to move the data from this byte into this byte. And in fact what we see is we've just got the 3-1 in there, which is actually what it was a couple of cycles previously. And then when we come to actually write the data to the IO port, we end up with 3-1 in there rather than the value that we'd actually read from here. So some changes that I did, one of the changes I did was just added a second read in here. And what this second read is doing is using the data that the CPU reads from here as the address to read. So what you can see here is this 3-1 here that exists from earlier reads here is actually being used as part of the read here. And so what this allowed me to do is to get to the bottom of what was going on. So what you can see here is this is the rule that defines this clock signal. We can see that the only inputs really used for this are the command, which just means that there's some sort of processor command, a read write to memory or read write to an IO port. A0 and A1 need to be 0 in this particular case because it's the lower byte, and we have this latched write read. So the only thing that was really dependent on this was this latched write read. And when you look at the table here, you can see that the difference between a memory code read and a memory data read, so this is between 4 and 6, is really just this value here, so the LDC as it would be. So what that got me to looking at is to see whether or not this could actually be part of the problem. And in fact, when you actually look at where this signal comes from, so the LWR comes down, is routed down to here, and then it was connected from here up to here. However, unfortunately, I'd actually plugged the end of this cable here, LWR, was going into LDC, and so this was giving us a bit of a strange situation. It took a little while to get to the bottom of, but once this wire from here was just taken from this pin to this pin, then everything seemed to be working okay. There's one other minor change as well, in that one of the PLDs, the PLD here, the test term, so this is used for doing factory testing. So generally when test is pulled low during normal operation, if it's pulled high, then it would allow testing in the factory to occur. So we're not really that interested in it. And the sign on these things was incorrect. So the sign's been corrected there, so that is now working. So those two changes have been done. And now when you look at the same trace, so you can see here, if we just go back to the earlier one, you'll see here that there is a missing green blip there and a missing green blip there for the 06 data read. And now in actual fact, with it fixed, you can now see that this is now occurring. And it was caused because the LDC and LWR connections were connected incorrectly, and it was affecting this clocking of the data. And you can now see up here that the data on the SD bus and the PD bus are both the same. You can see SD and PD there. So this seems to have actually corrected it. So I'm just going to now run the logic analyzers up, and we're going to power it on. Just power on system, and then we'll go and have a look at the logic analyzers. So this is the first one. So this is the power on self-test code. We can see that there's some values going up to the beginning here, but then when we actually start, you can see where the power on self-test write signal comes. You can see we've got 0, 1, 2, 3. So with each of the writes, we're actually seeing this change. So there's a few values at the beginning until we get into this sort of sequence, but you can see that we've got the sequence going all the way up to FF, and then it's going all the way up through the series, and then eventually it'll finish on FF there. So that's what we were expecting. This is about approximately 60k values that we would expect here. And these other signals here were the ones that I was using to help diagnose what was going on. So in particular, the things to be of interest is that up here we can see these are the byte enable signals. So these are the data buffers which are taking the 32-bit processor data and writing them out to the bus. So for example, BN0, for example, is when we're writing the lower byte out to the I/O port. You can see that this one goes low here. And these clock signals here, these are all the clock signals which are actually latching the data from the SD bus into the processor data bus. So by looking at all these signals here, I was able to work out what was going on. So I wouldn't pretend to fully understand what all these signals are doing, but now having actually got to the bottom of this, I understand this a fair bit better. And then what we can then see when we look at the traces here, the only thing to remember here is this is showing the lowest byte for the SD bus and the PD. So we won't necessarily see both bytes when we read it into memory. So when we're reading 2 bytes successively into memory, we'll only see the even byte here. And what we can see here is we read the code, we jump to the bit of code a bit further down, and then we read the value off of the address 0 in the ROM. And you can see now that we've read 0, and the processor data is also seeing 0. And then when we come to read the address using that data we've read, again is reading 0. And then when we come to write, we're then actually writing 0 out. And if we go a few along, we can see when we come to write this one here, you can see we've got 1 0 there, and we'll be writing 1 0 out there. So this all appears to be working. As I said earlier, I expected to be some problems, and obviously these types of things are quite tricky to get to the bottom of. But once you actually know what the cause is, it's dead easy. So that has allowed me to verify that we've got our power on self-test port working. That was a little diversion, but we wanted to get the power on self-test port working, and it's also helped us to sort out one of the bits of control logic that wasn't quite right. So in the next video, I'm going to start looking at building out the 32-bit 2 megabyte RAM board. Now this is almost as complicated as the control logic, not quite, but it's going to take a number of videos to do this. And we're going to be having sort of 32-bit wide data bus, so it's going to be quite a lot of wires to do there. So I'm going to break the video there. So if you don't want to miss out on future videos, then please hit subscribe. If If you hit like, it just helps to make the videos available to more people. And if you'd like to leave comments below, I do try and get back to you within a day or so. Thanks for watching.